So if we take, so on this Clausius-Clapeyron equation, so this is the equation, both Clausius and Clapeyron, two scientists came up with this equation as a way of predicting or calculating vapor pressure of a liquid. It's a rather difficult equation, so I'm going to show you this. So both of these versions work. So let's talk about this version down here. So this says P vape 1. So this would be vapor pressure at temperature 1. So some arbitrary temperature, temperature 1. Okay? Equals, now this is P vape 2. So this is vapor pressure at some other temperature, T2. So that's times, so this is exponential. When I write EXP, exponential. And this is a shorthand way of writing an exponential equation easier. So for example, if I write e to the power 2, so that's natural number e, right? E to the 2, a shorthand way of writing that would be exp bracket 2. So these things mean the same thing, okay? So when I say exp bracket of all of this junk right here is raised to the power. It's up into the exponential, okay? So what about this T1 and T2? Well, P vape 1 is the vapor pressure at T1, this temperature right here, okay? P vape 2, the vapor pressure at temperature 2, that's this temperature right here, okay? We have universal gas constant. Here we want to use the flavor of R, 8.314 joule per mole K. We have to use that version of R. And so our delta H of vaporization has to be expressed in joules per mole. Not kilojoules per mole, but it has to be joules per mole. Okay? So now what about this version of the equation? Well, both of these versions are the same. And what this version of the equation is, it's a little bit of algebra. So if you divide vapor pressure over to this side and take the natural log of both sides, you get this equation. And now if you plot the natural log of vapor pressure versus 1 over temperature, you get a straight line. And in fact, the slope of that straight line is, let's see, my pen did something weird. The slope of that straight line is the delta H of vape divided by the gas constant R. So this is actually how experimentally you can determine delta H of vaporization. You take a liquid, you boil it at different pressures and temperatures, right? So you pull a vacuum on it, and you slowly add heat. So maybe you might need to only boil your water at, let's say, 30 degrees. Well, whatever pressure it boils at 30 degrees, you make a data point. You move on to the next data point, right? And the next data point, and the next data point, and so on and so on and so on and so on. And when you fit this to a line, you can calculate the delta H, okay? What you also notice here is the steepness of the slope tells you what has the greatest delta H. So if you notice here now, water on this slope right here, so I'm going to say delta H of vape of H2O, we can definitely say is greater than the delta H of vaporization of, I'm going to write ETOH as my abbreviation for ethanol, because the line is steeper. It's just barely steeper, but it's a steeper slope. Oh, and I forgot to say there's a negative sign right there, which I think that I might have missed on my equation, but all the same, it's a negative slope, all right? No, I did not miss that negative sign. It's all good, okay? There's just a negative slope because of the natural log and 1 over t relationship. And so now we can definitely say that that is all greater than the delta H of vaporization of this diethyl ether. So that would be an ETOET. Don't worry about these abbreviations, okay? And so now, consequently, when we look at now this graph that I have right here, you can see because the delta H of vaporization of diethyl ether is the smallest, it boils at the lowest temperature, right? So it's crossing the line at 34.6 degrees. Ethanol has the second steepest slope. Consequently, it boils, in the middle. And then water has the largest delta H of vaporization, the steepest slope, so it has the highest boiling point. Okay? So let's do some calculations using this equation. And what's important to note here, in this equation, there's 1, 2, 3, 4, 5 variables because the gas constant R is a constant. So what you have to remember, to do anything with this equation, you have to know at least 4 out of those 5 things. So you can always get 2 data points on this equation by knowing the normal boiling point of a liquid. Why does that give you 2 data points? Well, because, for example, water boiling at 100 degrees, that means if, let's say, a T1 is 100 degrees, then that means P1 has to be 760 torr, right? And then if I wanted to know the vapor pressure at another arbitrarily selected temperature, then I can choose that. And really, I would probably want to choose P1 as my unknown, just because the way this equation is written out. So let's do some examples. Calculate the vapor pressure of water at room temperature, 298 K. Okay, fantastic. So we're going to use this version of the equation. P1 equals P2 exp bracket, and that's delta H of vape divided by R times 1 over T2 minus 1 over T1. So this equation is kind of a monster to use. So we're going to take it one step at a time. And the important thing we need to note is defining all these variables. So I'm going to say P1 is the one that I'm solving for. I'm free to choose, so you might as well choose to make it easy. So I'm going to say P1 equals an unknown, and it's saying calculate the vapor pressure of water at room temperature. So if P1 is what I'm calculating, then T1 is going to be my 298 K. All right. We have to look up the delta H of vaporization of water, and that would be given to you, or you would have the ability to look it up. It's 40.7 kilojoules per mole, so you don't have to memorize these delta H's. You can always look things up if you don't know them, especially things like enthalpy or entropy, or, well, now I'm speaking too much. Okay. So now we need to define P2 and T2. And I can technically pick any data point along this graph, but the easiest one to pick is the normal boiling point. I also recognize I have to be in Kelvin. So if water boils at 100 degrees, that's 373 Kelvin, right? 100 plus 273. So I'm going to say T2 is 373 Kelvin. And I'm going to say my P2 now has to be the vapor pressure that corresponds to that. And I'm going to pick it to be 760 torr. We could say 1 atmosphere. We could say 101,325 Pascal, right? We could really use any unit of pressure we want, because you notice here on this equation, when you divide pressure over to the other side, the pressure units will cancel. Okay? And so now we also know that R is 8.314 joule per mole K. Okay, so now I'm going to set up this equation, and I'm going to say P1 equals 760 torr times this exponential of all this stuff. So 40.7 kilojoules per mole, I have to make that joules, not kilojoules. So that's going to be 4.07 times 10 to the 4th joule per mole divided by 8.314 joule per mole per K. So that's delta H divided by R. Now I'm going to put myself a set of double parentheses to make sure that I get it right. Okay? So I'm going to say 1 divided by 373, end parenthesis, minus 1 divided by 298, in parenthesis, another parenthesis, another bracket. So I want to make sure that I get everything done correctly. And so if you have to piece this calculation together one step at a time, I fully recommend that. In the interest of time, I'm just going to show you what I get for this whole chunk, and you should definitely try to confirm that you get the same thing. All right? So when I take this number divided by this number times this divided by this minus this divided by this, well, you know what? Let's just go ahead and do it. I'll show you just so we get it right. So 1 divided by 373 equals 0.00268, and I'm going to go like 1 sig fig past what I need. Okay, minus 1 divided by 298. Equals 0.00335, let's say 6. Okay, so now I've got all of that. And now that's times this number divided by this number. Okay, so that's 4.07 e to the 4th power divided by 8.314 equals, and now that's 4895.4. 4895.4. I've skipped writing the units in to make this easier. And now that's around bracket, exponential of that times 760 equals P2. Okay? So now let's do all of that stuff. So if I say now 0.002681 minus 0.003356 equals, so it's a negative, that's part of where you get that negative slope, times 4895.4 equals, okay, great. So I'll rewrite that now. So that's P2 equals 760 times, and I'm going to, instead of writing this as EXP, I'm going to say that that's now become e to the negative 3.304. Okay? And I also know that all of the units, so technically all of the units inside this exponential go away. And so now whatever my unit is of pressure, that's going to be the unit of my final answer. So I've got this thing in the calculator, and on this scientific calculator, all I do is push this EX button equals, okay? That's not right. Let's try that again. So let's say I lost track of where I'm at. Let's see here. Okay, so let's say 3.304 negative E. Okay, that's it. And the reason I know that's the correct answer because the exponential of a negative number is always a number less than 1. And so now, so that was e to the power negative 3.304. And now I'm going to say times 760 equals, okay, 27.9 torr, and that's the correct answer. So that means water at room temperature. So I've got some room temperature water right here. Okay. Technically, I've got an ice cube in it, so it's not even room temperature. It's like much colder. But it only contributes like 20-ish torr vapor pressure. So that's a very low vapor pressure for room temperature.